We're given the vectored valued function r of t, which we'll call the position vectored valued function, and we're asked to find the velocity and acceleration vectors at t equals 1 and also the speed at t equals 1. So to find the velocity and acceleration vectors, we'll first find the velocity vectored valued function v of t, which is equal to r prime of t. Then we'll evaluate this at t equals 1 to find the velocity vector at t equals 1. Then we'll find the acceleration vectored valued function a of t, which is equal to the derivative of the velocity vectored valued function, or the second derivative of the position vectored valued function. And then we'll evaluate this at t equals 1 to find the acceleration vector, and then we'll find the speed by determining the magnitude at t equals 1 by determining the magnitude of v of 1. Because we'll also look at this graphically, let's also determine the point on the space curve where we're determining the velocity and acceleration vectors. So the point on the curve would be the terminal point of r of 1. So let's begin by determining r of 1. So r of 1 would be equal to, we'd have an x component of negative 5 times 1, a y component of negative 3 times 1 squared, and a z component of 4 times 1 to the 4th plus 3. So the x component would be negative 5, the y component would be negative 3, and the z component would be 4 plus 3, or 7. So this tells us we're determining the velocity and acceleration vectors at the point on the curve negative 5, comma, negative 3, comma, 7. And again, once we find these vectors and the speed, we'll take a look at this graphically. So now we'll determine the velocity vectored valued function v of t, which is equal to r prime of t. So the x component would be the derivative of negative 5t with respect to t, that'd be negative 5. The y component would be the derivative of negative 3t squared, that'd be negative 6t. And the z component would be the derivative of 4t to the 4th plus 3, that would be 16t to the 3rd. And therefore the velocity vector at t equals 1 would be v of 1. So we'd have an x component of negative 5, a y component of negative 6 times 1, and a z component of 16 times 1 to the 3rd. So our velocity vector has an x component of negative 5, a y component of negative 6, and a z component of 16. And now we'll determine the acceleration vectored valued function, a of t, which is equal to v prime of t, or r double prime of t. And since we just found the velocity vectored valued function here, we'll take the derivative of these three components with respect to t. So the x component would be 0, the y component would be negative 6, and the z component would be 48t squared, since 3 times 16 equals 48. And therefore the acceleration vector at t equals 1, or a of 1, would have an x component of 0, a y component of negative 6, and a z component of 48 1 squared. So we have components 0, comma, negative 6, comma, 48. So we answered the first two parts of this question. We found the velocity vector at t equals 1. We found the acceleration vector at t equals 1. And for the last step, we're asked to find the speed at t equals 1, which should be the magnitude of v of 1, or the magnitude of our velocity vector here. So the speed at t equals 1 equals, we'd have the square root of negative 5 squared plus negative 6 squared plus 16 squared. And now we'll go to the calculator to get our decimal approximation. So second x squared brings up the square root, and then we have negative 5 in parentheses squared plus in parentheses negative 6 squared and plus 16 squared. So the speed at t equals 1 would be approximately 17.8045 units per second if we assume time t is in seconds. Let's take a look at this graphically. In purple, we see the graph of the space curve. When t equals 1, this is the point on the curve. This tangent vector here is our velocity vector at t equals 1. And this light blue or light green vector here is our acceleration vector, a of 1. I hope you found this helpful.